this is the first event we've run from our CBT in whatever it is, 2 years or something like that. I mean, the first non-UCL, outside of UCL event. So this is a kind of a, hopefully the first in the series that we will be running over the remainder of the CBT. Just a couple of things as well. I think I said briefly last night, one of the main things, at least for me, that we want to get out of this is exchange. Okay, so there are, of course, going to be presentations, there are going to be talks, etc. But it's really about you guys. It's not so much about information exchange. It's about you guys learning about each other, what your interests are, rather than us giving the presentation so much. Today we have a fairly packed program, but I hope it's also quite relaxed in the sense that there should be time to ask the speaker questions. Please don't be shy in standing up yourself if you don't understand something. Just, I think, jump in and keep it informal. Okay. So this session this morning is going to be recorded. So I think we've got Reuben up first, right? And then we've got Changmin online. So I think, Reuben, you've got to say half an hour, roughly?
Yep.
And you want half an hour, do you? Or
with 5 or 10 minutes of questions.
So 25 plus 5?
Yep.
Or is it? Okay. Great. All right. So, Reuben, do you want to come up and introduce yourself, and we'll do the first presentation.
Okay, so I'm at UCL on the FAI CBT, and this is work I've done with my supervisors, Shawe-Taylor and Guedj, on controlling confusion via generalization bounds. It's a bit technical, but I'm going to try and make it a bit more approachable for a more general audience of machine learning experts. And we'll see how that goes. Okay, so first of all, what are PAC-Bayes bounds? We start defining the true error. So the true error is not quite the test error, it's the test error on a hypothetical infinite test set. Or you can think of this as the error in expectation over the data generating distribution. And then the generalization error, normally it would be the gap between your training error and your test error, but now it's the train error and the true error, right? So the true error with this infinite sample size. So if your generalization error is low, that means you've learned something that generalizes the data the algorithm hasn't seen before. And then a PAC bound, so PAC stands for probably approximately correct, which sounds like one too many words, but hopefully I'll be able to explain it. So a PAC bound either says something like, with high probability the true error is small, or with high probability the generalization error is small. Okay, so if your true error is small, that means your hypothesis usually gets the right answer, right? So it's approximately correct. But you can't guarantee that, because there's always a chance of getting an unrepresentative sample, and so you can only say that the result of your algorithm is a probably approximately correct hypothesis, right? So it's not guaranteed to be correct, it's only probably correct and approximate. This one doesn't really map to the PAC acronym because you're talking about generalization error now, and if your generalization error is small, that doesn't necessarily mean you're approximately correct, but I'm still going to call it a PAC. Sorry about that. So then there's PAC-Bayes bounds. That's a type of PAC bound that's inspired by Bayesian machine learning, but it's not limited to Bayesian machine learning. And it's not Bayesian either. It's a total misnomer at this point. It's a frequentist bound just inspired by Bayesian machine learning and applicable but not limited to Bayesian machine learning. Okay, so that requires some more detail. So the setup is, let's stick to neural networks for classification for the moment. So the setup is an input or feature set X. So that's like your set of images, or sorry, not your set of images, that's a sample, but the space of all possible images. And then we've got a finite label set and a data generating distribution on the Cartesian product. So from D, you can sample pairs X, Y. So that's an image and its label. And for example, this could be a probability density over the Cartesian product, but not all distributions have a density, so I'm just going to say the data generating distribution and not talk about densities. And we've got a fixed neural network with parameters W, and there's D of these. So these are the learnable parameters of the network, the weights and the biases. And then I'm going to denote by HW the function that you get with the neural network on weights W. Okay, so every neural network calculates a function. The weights of W, that function is called HW. So now for a fixed weight setting or parameter setting W and a fixed sample S, we can define the empirical error probability. So that's the fraction of the sample on which you're making an error, right? So this is the classifier's predicted label, and this is true label, and then this indicator tells us we've got it wrong, and so you count up how many times you got it wrong and divide by the sample size. And then the true error would be this over an infinite test sample, but that's equivalent to just having the probability, right? So the probability, if I draw a new data point from my data generating distribution, that HW misclassifies it. So then a learning algorithm is an algorithm that takes in a sample X and spits out some weights of the neural network, WAS. And we would like a theorem, this would be a PAC-bound, saying with high probability, the true error on the left, the true error of the outputted weights is bounded by the empirical error probability plus some small epsilon, right? So usually you've got your training error, and it goes down to 0 often, and then your test error will be a bit higher, and then this will be saying it's a most epsilon higher with high probability. But it turns out this is really hard, at least in the overparameterized regime, so deep neural networks. So we can get bounds like this when the VC dimension is fairly small, but once you're in neural networks where the number of parameters may be an order of magnitude or two larger than the number of data points, you just can't get enough data points to get a PAC bound like this involving the VC dimension. And the other classical bounds fail in this regime as well. So we have to generalize. Instead of having a point in weight space and saying, okay, what's the error probability for that? We'll take a whole distribution over weight space and ask what's the error probability of that. Okay, so this triangle means the set of distributions. So how would we classify it according to a distribution over weight space? Well, the idea is if you've got a distribution, the stochastic classifier HQ classifies by first drawing weights from Q and then classifying according to HW. The important point to note here is a different W is drawn for every classification. So you can actually classify the same point twice and get different answers. That's what makes it a stochastic classifier. And then these are the old definitions for a fixed weight, W. And the new definitions, you just take the expectation over W. Right, so the empirical error probability, this is a fraction of the sample on which you make an error, now turns into the expected fraction of the sample on which you make an error. And this, the expectation, if I write it out, then it's the probability when drawing a new data point and a new weight from Q that you make an error. Okay, so just think of it as the true error and the empirical error still. So we can now get a theorem saying that the true error is bounded by the empirical error plus some epsilon. These used to be just weights. If I go back, it used to be just weights at the bottom, and that was not possible in the overparameterized regime. And with distributions, it is possible. Okay, so here's an example of a PAC-Bayes bound that works in this overparameterized regime. So for any prior P, just call it a prior, forget I said that. It's just a distribution, it's a reference distribution if you want to call it something. And any delta, that tells us how confident, how probably we want our PAC bound to be. And sample size M, and stochastic classifier, which remember takes in a sample S and spits out a distribution over weight space. We can say that with high probability, so with probability at least 1 minus delta, so our delta is small, over the sample size, we get that the KL between the true error, sorry, the empirical error and the true error is bounded by something. And just imagine this as B, right? It doesn't matter what the exact form is. All that matters is it's only in terms of empirical quantities, so we can actually calculate it. Okay, so now you're thinking, okay, but why is there a KL here? I thought we were going to get a bound like that, not a bound that said the KL was small. So saying something like this is equivalent to saying, or roughly equivalent to saying that the true error and the empirical error are close. Now these two are probabilities, right? So if I imagine them as coin tosses, I can take the KL divergence between those two distributions. So that's what I've got here, a coin toss with the empirical error and a coin toss with the true error. And I'm saying that their KL divergence is bounded by something small. So this turns out to be a small thing if you do it right. So this is saying that the empirical error and the true error are close, right? And that gives you a bound on the true error. So first thing to note, again, it's not Bayesian. I accidentally said prior for P. It's best, although it's called a prior, it's best to not think of it as prior and just a reference distribution. It's just any distribution that's chosen before you see the data. So because it holds for all D and all P, it's actually a frequentist bound. There are tricks for choosing a good P, and that's a whole other talk, so I won't go into those, but it is a big part of PAC-Bayes. And then, as I said before, this says that they're close, and then this gives you an interval in which ED can lie. So you've got your point ES, the empirical error, and then you're saying ED is close, so it's within some interval, and then this gives you some upper bound on ED, the true error. And the right-hand side is calculable. It's only known quantities. So the really cool thing about this bound is that it holds for all stochastic algorithms. Any stochastic algorithm you want, you'll get a bound like this. How can that be? Well, the size of the bound is in terms of that algorithm. So the size of the bound adapts to what the algorithm does or how well the algorithm performs. But the interesting thing is this bullet point here. This gives an upper bound on the true error. I can actually choose the algorithm, the stochastic algorithm A, to minimize that upper bound. And I will still get a valid bound at the end of that. It will still hold with high probability. I'll talk a bit more about that in a bit. Okay, so how would we actually use Mauer's bound? So let's suppose we're doing three-class classification. So we've got a dog, cat, and a bird. And this is our empirical confusion matrix. So 1% of the time we mistook a bird for a dog. And then you condense this. So the diagonals are where we're being correct. So that's 0.79. And then the off diagonals are where we're incorrect. So this is the empirical error probability. And then you plug this into your PAC-Bayes bound. So the bound, remember, just says the distance between the empirical and the true errors is small, less than some b. And then that implies some bound on some interval in which the true error lies. That's easy to calculate, but I won't go into it. Okay, so what do we get in general? In general, right, so for not particular empirical error, but just some arbitrary ES, then the bound implies that the true error is less than or equal to some constant. And this constant is in terms of all of these things. Doesn't really matter what they are. What it matters is that they're empirical. All of those things we know. And so we can actually choose our algorithm to minimize that bound. So the algorithm is A maps S to the distribution that minimizes this bound. Okay, and that's a perfectly legal algorithm. You can use it for training, and then in addition, you will get a bound at the end. So this is the power of PAC-Bayes. You can use all of your data for training and getting a valid bound at the end. The drawback is that these bounds are not fantastic at the moment. They're way better than they used to be. They're roughly within a factor of 3 of the actual true error, if you take an actual big test set. That's a massive generalization. It varies a lot depending on the circumstances, but the bounds are not super good, but they have progressed massively in the last few decades. Okay, so Mauer's bound has a weakness that our paper addresses. And that is, we look again at the empirical confusion matrix, we can see that some of the errors are much bigger than others, but the bound doesn't tell us anything about that. Bound just compresses all the errors into one empirical error probability and then bounds the true error probability. And we would never know that most of the time we're just confusing cats and dogs, and this one twice as often as this one. So how do we get a bound that does capture that information? So we lose detail in individual error probabilities. So the goal is to find a bound or a theorem that says that with high probability, the true confusion matrix with an infinite test sample is close to the empirical confusion matrix. And I'll define close in a second. The key idea is to note that these empirical error probabilities add up to 1. Something has to happen. And so that can be interpreted as a distribution on 9 points. And so can the true one. And so we can measure their distance or their divergence using KL divergence. These two are distributions, and the same thing, we'll just measure the KL divergence. So note the bold E, before it was just one error probability, now it's a whole matrix of error probabilities. And some of them are not even errors. The diagonals are correct classifications, but we'll just put it all into a big bold E. Okay, so what does our bound say? So this is Mauer's bound, the old one, with the non-bold E, and then our bound says that under the same conditions, you can bound this KL now between these bold E's by this mess. It's admittedly a mess, but the important thing to note is that all the quantities are empirical again. So capital M is the size of the dimension of the confusion matrix, M is the sample size, delta is your confidence level, etc. We know all of these things. Sorry, that should be a QAX. Okay, so how are we going to, oh yeah, the upshot of this is it just tells you the KL between the empirical and the true confusion matrix is small. It's bounded by some B. And from this, you can derive a few other bounds that also hold with high probability. Okay, so to visualize it, let's drop on the bird class and just go to cats and dogs. And then we can plot this on the simplex. So I'm going to collapse these correct classifications into this point here. So this point here is the probability that we correctly classify, which is the diagonal element sum. And then this is the probability that we predict a dog, it's actually a cat, and predict a cat when it's actually a dog. So then we can plot our empirical error probabilities roughly there. And now what does our bound say? It says that the true error probability lies within some region, right? If you plot a level set of the KL divergence, then you get some convex region like this. And the convexity is really great because it means we can find a worst case. So if we have some loss vector L, so this is user specified, right? It tells you how bad each of the error types are. So ideal would be if the the true error was right down in this corner. But if you go away from the corner, maybe going in that direction is much worse than going in that direction. And so L points more upwards than left. Then I can say, okay, well, that would be the worst direction in which the true error could lie. And so that's the worst case true error, the one that's furthest in that bad direction. Right, so what can we do with this? Well, the empirical error is a known quantity. The true error is unknown. It lies in this green region. But the worst case true error is a known quantity. That's empirical. We can calculate it. It's just that point up there. And with more good news, this worst case true error is actually differentiable in the neural network parameters. And so this inspires our algorithm, which is that A maps S to a distribution that minimizes the loss vector, the dot product of the loss vector and the worst case true error. Right, so if the worst case true error is up there, and then I dot it with the loss vector, that tells me how much loss I'm incurring with that true error. And then this tries to minimize that. So that's the algorithm, that's the bound, and there's one tricky bit left. You'll note that the bound contains this awkward KL term, and so getting the worst case error involves inverting this annoying KL term and then differentiating it, which is quite awkward, but it just turns out to be Lagrange multipliers with some extra stuff, and that's the proposition that gets it for you, but I won't go into the details of that. Yeah, I think I'll leave it there. Thank you. Any questions? Yeah.
I think you said at the beginning that when you say distribution weight space, it's the point to get this bounds.
Yeah. Yeah.
Can you explain again why that is?
Okay. So there are slides on that. So this is the classical generalization theory, where if you increase the capacity of your hypothesis class, which is equivalent to, say, adding parameters to your neural network, then the bias will decrease, but at some point, the risk will decrease, and then at some point will increase again. Right? If your hypothesis class is really enormous, or your network is really enormous, then it can fit anything. And so when it does fit your data, it's not really evidence that it's generalized. At least that was the classical understanding of it. And these VC dimension bounds would incorporate that kind of thinking. And so the generalization bound would just be enormous, like 1,000,000%. And that's not an exaggeration, which was completely vacuous. And then the modern thinking is that there's some interpolation regime at the point where you just about manage to fit your data. And then if you increase the number of parameters further, then the risk decreases again. And this is just unexplained at this moment, as far as I'm aware. So PAC-Bayes goes some way to explaining it, but it doesn't fully explain it. Does that answer your question? No. Ask it again.
I think his question was about, you need a region, right, of weight space to integrate over, rather than a point space. Rather than point, right? I think he was asking about,
so
what? Well, I don't know quite what the question was, but maybe questions might be, how do you find that region? Maybe, but you could read that question.
I'm not sure I actually fully know why you have to generalize to distributions over weight space. I think at this point the answer is it works. And there's you can talk to Felix, he's managed to get some bounds where you don't do that. But they're close to 100%, so they're not great at the moment. Yeah, I think we don't really know.
Thank you.
Yeah.
I might have a question related to this topic, because it's a little bit counterintuitive that going to distributions might help, because it's more general than just considering points, right? We can always just pick like the delta distribution. It's the same thing as just having one weight. My question is, if I do that sort of trick, that means that the bound that you get is going to get larger, right? If I have a distribution that's very broad of weights and one that's very sharp, how does that change the actual bound?
Okay, so we just look at Mauer's bound. The value of this bound depends on the distribution you pick. And you could just pick the distribution equal to P, and then this KL would be 0. And that would be the smallest you could get it. And that tells you that your empirical and true error are close together. But it would also make your empirical and your true error terrible. It would make both really large. So there's this trade-off between, okay, how far from P do I allow Q to stray? That will hopefully reduce the true error, but at the expense of weakening the bound. So yeah, you could put point distributions in. Actually, you can't put a point distribution in, because then the KL will be infinite. Right? Yeah, so it's not a bound. If the bound depends on the distribution you pick, that's why it changes. That's probably what happened.
Could I just ask one quick question? So you, at the end, you had this lovely example of birds and dogs, whatever it was. the kind of the missing thing here was like, I was expecting you to say, and therefore you see, if we do this thing where we now move in this direction, it's good. You know, you're gonna maybe show us some empirical results where using your in your defense, defense of this area, is there, you know, a simple explanation as to why not, or you just didn't get around to it, or is it not really working out, or is it?
I think if I had a week more, I would have got the experiments running. It's a work in progress.
All right. Well, thank you, Reuben.